So now that we're familiar with the F distribution and the range of ways that we can work with it and calculate critical values, we're going to make use of that within a hypothesis test. Now, a lot of the features, a lot of the anatomy of a hypothesis test will be exactly as you would expect, exactly as you're used to, but we'll fill in and look at some of the specific differences when it comes to working with an F test. Firstly, we want to try and collect all of the variables that are going to be relevant to the question. We're going to look for the n value, we're going to look for the sample variance, and we're going to look for the degrees of freedom. Degrees of freedom just being one less than the n value. We're going to do this for the first distribution. Here I'm going to refer to it as distribution x. And we're going to do a similar thing for distribution y. So I always start with trying to pull all of these values which will be used in the hypothesis test. This is a good time to set the significance level, and we are told to test at the 5% level. Next, we'll go ahead and we'll set the hypotheses. In this particular question, we've actually been given the hypotheses to use. So my null hypothesis is that the variance of distribution x equals and is the same as the variance of distribution y. Now this is always going to be the default null hypothesis for an F distribution hypothesis test. So whether it's given to you or not, this is always the null hypothesis, and the context is going to indicate what the alternate hypothesis should be. The alternate hypothesis is that the variance in distribution x is actually larger than the variance in distribution y. Okay, so all of this is really going to be pulled from the context of the question, and we should be ready to start actually processing our hypothesis test from there. I'm going to get a diagram, just going to make sure that I mark 1, and I'm just going to shade in the critical region, the 5% region off in the top end of the tail. Now, I want to know what is the critical value. What is the value that if it's exceeded by our test statistic will give a significant result? So I'm just going to find the critical value for F and the 2 degrees of freedom, so 12 and 8. 5% significance level gives me 3.28. The test statistic for the F distribution is simply s squared of x over s squared y. So one sample variance over another sample variance. In this case, I get 1.33. This is outside of the critical region. It is not a significant result, and we draw our usual conclusions from there. So hopefully you can see the anatomy and the steps that we go through in the hypothesis test are very familiar. The differences come in the hypotheses, how we calculate the critical value, and how we calculate our test statistic. But the use of the diagram, the use of the conclusions, all of that remains consistent. Okay, let's go ahead and have a look at another example here. The difference here is that the alternate hypothesis is that variance for the x distribution is less than the variance for the y distribution. Okay, let's go through our normal steps. We're going to collect all of our variables. These will all be able to be drawn from the context of the question. We're going to set our significance level at 5%, and then we're just going to state our hypotheses. Now, on the diagram, I'm going to shade the critical region off in the left tail. So let's just anticipate the critical value that we calculate should be a value smaller than 1. I'm looking for a value below 1. So I need to find a value for the F distribution with degrees of freedom 6 and 10 that is exceeded by 95%. We know that this is when we do our reversals. We do the reciprocal of an F distribution 10, 6 and 5%. That's 1 over 4.06, which gives us a critical value of 0.246. The critical value here, 0.246. Okay, just as I was expecting. The test statistic now, I'm going to do s squared for x over s squared for y. 5 over 25, we can do that in our heads. That gives us 0.2. This is a significant result. Significant result means that we have sufficient evidence to reject H0. Some people like to stay working in the right tail, and to do that they kind of manipulate the diagram and the critical value that they calculate. Now, this is a valid technique to use to conclude or to draw a conclusion in the hypothesis test, but to me it does seem counterintuitive. But just so you know, because you may see this in mark schemes and in other examples elsewhere, I'll show you what that looks like. So, if we were to calculate the critical value with 10 and 6 as the degrees of freedom, we would get 4.06 as our critical value, and we're actually going to divide, or we're going to calculate our test statistic the other way around. We're going to do s squared of y divided by s squared of x, and that gives us 5. And 5 is similarly in the critical region, and we once again have a significant result, and we conclude that we have sufficient evidence to reject H0. For me, this isn't as intuitive as the original way that I've shown you, and it's not so consistent. You really just need to make sure you're paying attention to which critical values to use, you're paying attention to which degrees of freedom you need to use, and I'm not sure there's that much benefit when we know how to calculate and deal with critical values in the left tail. Okay, let's talk about one where we have a two-tailed hypothesis test. As usual, just going to gather all the important variables right at the beginning, our n value, our degrees of freedom, and our sample variance for each of the two distributions being worked with. Hypotheses are given to us once again. Since this is a two-tailed test, just as with all our two-tailed tests, I'm just going to represent both of the potential critical regions. So 5% in the right tail, 5% in the left tail. Okay, I'm going to want to find the critical values from here. So let's go ahead and find a value for our degrees of freedom that is exceeded by 5%. We get 2.75. Let's go ahead and find a value that is exceeded by 95%. We'll do our usual reversal manipulation, and we get 1 over F1210, 0.05. It's 1 over 2.91, which is 0.3436. So I've marked off both my critical values, and I know anything that is more extreme than those critical values would be a significant result. Let's go ahead and calculate our test statistic. We get 1.6 over 2.4. I think you might recognize that this cancels down to 2/3, 0.66 recurring. This is not in the critical region. This is outside of the critical region. So we do not have a significant result, and we do not have evidence to reject H0. Once again, we'll follow through with our usual conclusions, both mathematical and in context. Okay, and then just the last type that I want to go through with you is a bit of a non-typical example. The data that we've been given are the sample size, the mean, and we've been told the sum of squares about the mean. The sum of squares about the mean is going to be the sum of x minus x bar squared. And if you recognize, that is actually the numerator of the formula for the sample variance, the formula for s squared. So it's the numerator. If we divide that by n minus 1, we'll have our expression for s squared. Okay, so I've got all the values for outside and all the values for inside, and we can go ahead and process our hypothesis test. So just the extra step here is that the data wasn't really given to us in the way we've seen so far. We had to generate the sample variance for ourselves. Okay, let's process the hypothesis test as you would expect. And the underlying assumption when working with the F distribution in a hypothesis test is that the original distributions are normal distributions. So the sample data that we've collected has come from populations which are normally distributed. Okay, so this is a fundamental underpinning assumption around the F distribution. It does not work for non-normal distributions. All right, so just make sure you pick up that mark by being really clear and specific about that. Okay, so here's a variety of different hypothesis tests that you will have. As I've said before, the process should be quite familiar. We just need to throw in the specifics of how to calculate the test statistic, how to calculate the critical value, and obviously what the default hypotheses look like. Make use of that diagram. The diagram can help to add clarity to the way